sharing my screen. And, oops, this isn't your class. This is, when last we met, we had left off in trying to make a box plot of these values, which were the ages of people who were with us on Friday. Before we pick up there, though, I'd like to, somebody over the weekend emailed me a question about one of the activities, and I believe it was activity 3. And so activity 3, I like because I think it's a very tactile, hands-on way of dealing with the idea of finding mean, median, and mode. What I want you to be careful with is when you do this, they already have worked out for you the example that makes use of these 5 states. Do not use those 5 states. When you do it, you're not just repeating exactly what they did, but instead they want you to use the states Arizona, Hawaii, and so on. And so you're actually going to make use of these states. And so you're going to replicate the work that they do, but with these states. And if you don't have access to graph paper, I do believe there is graph paper available for you in the handouts for activities in Blackboard, so that you're going to want to take each state and just put one letter in a square. That way, when you line them up, we're not worried for this first one about what the letters are, but the number of letters. And so you're looking for that strip, that length of strip that occurs most often. Then for the median, they want you to take another strip. And if we look at their examples, Nevada had 1, 2, 3, 4, 5, 6. Montana had 7. Virginia had 8. Wisconsin and Minnesota had 9. So to find the median, they want you to take another strip and fill in those numbers. And we had said the median was the middle value. And so they want you to find the middle value by folding that in half. Again, you don't want to do it with these states, but rather you want to do it with the Arizona, Hawaii, Ohio, Maine, Oregon, Idaho, Texas, Louisiana, and Kentucky. And the median, again, is the middle of the list. And then for the mean, they want you to say, okay, so I've got these strips for my states, and they all have different numbers number of letters in them, different numbers of values. I want to try to divvy it up evenly so that they all have about the same. And when I divvy it up so that they all have about the same, you see that the mean would be just a little bit less than 8, because most of them have 8, only one has fewer. And that's kind of the one way of looking at the idea of mean. An example where I think this might be an interesting approach to mean is, let's say you have a table of kids and you give each of the kids some cookies. And so let's say we give this person 5 cookies, give this person just 1 cookie. We give this person 8 cookies. And we give this person 2 cookies. And it doesn't seem fair. And so we instead might want to say, okay, What if you guys wanted to make it fair and have everybody have the same number? Then we'd put all of the cookies together in the middle of the table. And we'd have one big pile, and we try to divide it evenly, pass them around, and share them so that everybody had the same amount. Well, if I add, this pile in the middle would have 16 cookies, and so everybody would have 4, and that would be my mean. Just kind of a hands-on way of looking at the idea of what does that mean? What does that average mean? Something like this where we'd maybe want everybody to have the same amount. But instead of doing that with cookies, we're doing that with the number of letters in the names of the states. Then last one, they want you to see how does the mean, the median, and the mode change if I change my data set. So they're asking you to add Massachusetts to the set of states that you were working with and see how that changes the mean, the median, and the mode. Then they want you to take out Massachusetts and add instead Maryland, Michigan, and Oklahoma and see how that changes the mean, the median, and the mode. Okay? A little bit better with the directions for that activity.
Yeah.
Okay. And what I like about it is because usually we look at, mean, median, mode as kind of being, very numeric, mathematical ideas. And here we're taking them into looking at how many things we have and how we can share them, how we can divvy them up. So, all right. Then, if that's all right, we left off on Friday. Well, no, I apologize. I'm rushing and I shouldn't. Besides that question that I received on that activity, does anybody else have any other questions on any of the activities? Or has anybody started looking at any of the homework problems? Does anybody have questions on any of those?
I do have a question on the activity, and I think I have a question on the homework. I gotta look.
Okay, which activity?
I'm in NEM activity. I might not have just wrote it down, but for graph number 2 and the bar graph, what are we counting by? Because it says each circle represents blank M&Ms.
You decide. You get to decide.
Okay.
Whatever you think is appropriate. Okay?
And then do the bar graphs, do those touch?
Bar graphs do not have to touch. Histograms have to touch, but bar graphs do not.
Okay.
Okay?
And then I just gotta look for the math question.
Okay. Well, I've got my textbook open. Does anybody else have any questions, Jay?
It's number 30 for page 697.
Okay. Right, question number 30 says, oh, you know what? We have not yet gotten to the standard deviation. That's where we're going today. So are you all right to leave this question open? And after we define standard deviation and look at some examples at the end of class, we'll go back and look at it.
Okay.
Okay. Any other questions?
That was it that I had.
Okay. Then let's look at this. Does everybody have this list of our ages from Friday? We were going to find the quartiles. And so let's see, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And so the median would be midway between the 19 and the 20. So that would be 19.5. And then for the lower quartile, I'd look at this bottom half. And here, the middle of the bottom half would be 18. And for the upper quartile, I'd look at the middle of the top half. And for the upper quartile, that would be 25. So now if we were to draw a box and whisker, our number line would have to go from 18, let's go 20, 30, 40, 50, 60. So this would be about 15, 16, 17, 18, 19. Our lowest value is 18. Our lower quartile is 19 and a half. I'm sorry, I take that back. Our lowest quartile is also 18. So that's going to be going through the dot for the same values. Our median is 19 and a half. So that's our upper quartile is 20. So we've got this tiny little box. And then our maximum value is way out here, 61. And as I look at this box plot, the way it's drawn, doesn't it look like, well, there's a whole bunch of people down here, but doesn't it look like the way this is attached, that there might be several values in between? And are there several values in between? No. So let's look and see if we have an outlier. And to decide if we have an outlier, remember the first thing that we wanted was our inner quartile range, which was our upper quartile minus our lower quartile, which would be 20 minus 18, or 2. And then we take 1.5 times the inner quartile range, which would be 1.5 times 2, or 3. And so if I take the lower quartile, 18, and subtract that, I get 15. So anything below 15 is an outlier. And I'm going to take 18. I'm sorry, not 18. I apologize. Our upper quartile, which was 20, plus 3 to give me 23. And so anything above 23 is an outlier. And so I guess that means I'd be an outlier as would the 25. They're significantly further from the rest of the data. And so for this box and whisker then, if I wanted to show outliers, I'd again have my number line. My minimum in my first quartile are 18. My median is 19 and a half. My upper quartile is 20. And then those other two, to show that they're outliers, I would just put points, but not connect the points. I'm going to not attach them to the whiskers. Which makes this a very unusual box and whisker, because the ends of our whiskers are the boundaries of our boxes, but then we have a couple outliers. And do you see how this more realistically represents our data than that first box and whisker, so which made it look like there were many more older folks than there were. And so this idea of finding the inner quartile range, multiplying it by 1.5, subtracting it from the lower quartile, and adding it to the upper quartile, and anything that's not in between those numbers would be considered outliers. Instead of doing the computation, for a much more intuitive approach, I can look at the width of my box, and anything that's more than 1.5 times the width of the box away would be an outlier. So this idea of making a box and whisker, either without outliers or annotating, marking the outliers as separate. Is everybody all right with making that box and whisker? Is everybody all right with that process of finding your quartiles and your inner quartile range and your 5-number summary? Any questions? If not, backtracking, all of that started when we looked at measures of dispersion. And we looked at these 3 students and their grades and said, well, if I just looked at the middle, mean and median are the same, but the students aren't the same. We said the first measure of dispersion was the range. The second was this idea, when I look at these box plots, they give me an idea of the spread of my data. The next one that we're going to look at, that next measure of spread, is something that's called the standard deviation. And before we look at that standard deviation, we talk about something that's called the deviations from the mean. And the deviation, well, the deviation is a difference. So that's the difference, which comes from subtracting the data value minus the mean. And so if I have a data set with 5 values, I will have 5 deviations. And so I'm going to backtrack just a second and copy these students' grades. Because I want to make use of them down here. Hopefully it's going to let me move that off to the margin here. And so if I look at student A, I'm going to make a table. In the first table, I'm going to label it as X sub I, and X sub I are going to be my data values. And for student A, their grades are 80, 83, 85, 87, and 90. And at the bottom, I'm going to put one more row that I'm going to call total. And the total of those grades was 425. And then we found the mean. And so I'm going to make another column here, and I'm just going to put the mean in. The mean is 85. And so then to find the deviations, I'm going to take the value and subtract the mean. So it's the value minus the mean. So I'm going to label this X sub I minus X bar. And again, that's how we're defining our deviations. So 80 minus 85 would be negative 5. 83 minus 85 is negative 2. 85 minus 85 is 0. 87 minus 85 is 2. 90 minus 85 is 5. And so those are my deviations. Now, if I look for that standard deviation, that's like an average. I'm going to put that in quotations, though, of the deviations. And so if I wanted to take the average of the deviations being this column, well, in order to take the average, I'd have to add them up. When I add them, what do I get? Can somebody add that column for me? Nobody's doing the addition for me. Come on, you guys, I need some help here.
Sorry, I'm taking the notes.
All right, then it's a good, let me know that I should talk slower and write slower. Let me know when somebody's got those at it. We'll wait to make sure everybody's caught up. I'm sorry, what did they add to?
Okay, what are we adding?
The deviation column.
So the -5, -2, 0, and 2 and 5.
Yes. What do those add to?
0.
0. Wait a minute. How can I take the average of a set of numbers if they add to 0? That doesn't make any sense. But if I stop and think about it, if this mean is actually a measure of the middle, doesn't it make sense that there should be as many numbers, much value above the middle as there is below the middle? And so the sum of the deviations, and this is going to be a question in the homework, the sum of the deviations is always 0 or approximately 0. Why do I say approximately 0? Can you picture some of the examples that we did in class already where we had to round off to find the mean? If you have to round off, the deviations might not add exactly to 0, but they'll be close to 0. And so I'm going to apologize, you guys. I'm going to finish writing on the rest of this page. These things I will put on a blank page and look at later, probably on Wednesday. So since the sum of the deviations is always 0 or approximately 0, what we want to do to take care of the fact that some are positive and some are negative is we're going to square the deviations. We're going to take the data value minus the mean and square them. So my next column is going to be the data value minus the mean squared. Now that looks like a lot of work, but really all we're doing is we're taking the next door neighbor, next door number, which was my deviation, and squaring. -5 squared, you have to remember that that column, they should all be positive, because remember your rules for signed numbers. When you square a number, you multiply it by itself, and negative times negative will be positive. So this next one will be 4. 0 squared will be 0. 2 squared will be 4. 5 squared will be 25. Then we're going to total the squares, which means I'm going to add up that column. And that column will add to 58. And so that's the column we're going to take the average of. So then we're going to divide the total by what's called n, which is the number of values. And so I'm going to take that 58 and divide it by 5. And doing that, I'm going to get 11.6. But now wait a minute. That 11.6, doesn't that seem really strange as a way of describing the spread of these numbers? It's too big. So what did we do that made the numbers big?
Square root.
We squared them, right? So we're going to have to take the square root. So after we divide, we're going to take the square root. And this process of taking the square root is something that I don't think anybody does by hand anymore. And so this is why for this section, you do need a calculator. And so with my calculator, when I take the square root of that 11.6, I get that my
4058.
Beautiful, but only round to 1 decimal place because that's our rounding rule. So our standard deviation is 3.4. So when I look at the standard deviation, I look at it as a process. You sometimes see the standard deviation written as a formula. Is everybody done with this page? I'm going to turn to a blank sheet of paper and do a lot more writing about the standard deviation. Is everybody done with this page?
Yeah.
So the standard deviation is usually abbreviated with an S. And in order to find the standard deviation, the first thing we had to do was find the mean. Then we subtracted the mean from each value. Then those values that we got by subtracting, we squared. Then we added up all those squares. Then we divided by the number of values. Then we took the square root. And so if you wanted as a formula, there it is. We're going to look at it more as a process. And so to look at it as a process, we just found the standard deviation for student A. Let's find the standard deviation for student B. And again, I look at this as a process, and I think that making a table to help us find it keeps our thoughts a little bit more organized. First column are the values, the grades, 100, 95, 85, 75, and 70. We already added them up to 425. And so we said our mean was that 425 divided by the 5 numbers gives me 85. To that point, is everybody okay? Or am I going too fast?
I'm good.
Then our next column is going to be the mean. I like adding that as a separate column. While it looks repetitive, it always helped me, because then after that, I'm going to find my deviations, the value minus the mean. And then I'm going to square my deviations, the value minus the mean squared. I know with the first example, we didn't fill in the table horizontally because we still had to build it. But I'm going to just go straight across. 100 minus 85, 100 minus 85 would be 15. And 15 squared would be 225. What's the next one? 95 minus 85 is 10. Squared is 100. 85 minus 85 is 0. Squared is 0. 75 minus 85, that would be negative 10. Squared is 100. 70 minus 85 would be negative 15. Again, remember, no matter what your calculator tells you, when you're squaring a number squared should always be positive. So that's positive 225. I'm going to do a quick check. This middle column should add to 0. If it's not 0, it should be pretty close to 0. This next column, could somebody please add that for me and tell me what you get?
650.
Beautiful. So now we're going to take that 650 and divide it by the same thing we divided by for our mean. So when I take 650 and divide it by 5, what do you get?
130.
130. And the standard deviation is the square root of that. And so here's where, again, you need that calculator to find the square root. And the square root of 130 gives me 11.4. And if we compare student B to student A, we saw that student B had a larger range, a bigger spread in value. And do you notice there's a larger standard deviation? So the more spread there is in the data, the larger the standard deviation. And so we haven't looked yet at student C, and student C's grades were 100. Well, let's shrink this just for a second. 100, 55, 85, 85, and 100. And just because I want to make sure you guys got this process down, I'm going to ask you to please find their standard deviation. So we want their scores, their mean, their deviations, and the deviations squared. And I'm going to give you folks a minute to find that. How are you folks doing?
Good.
Good. Did you guys all finish or not yet?
Yeah.
Yeah. Did you get that standard deviation was 16.4? And do you notice that that student had a bigger range, had a bigger spread in values, and so they have a higher standard deviation. So the closer the values are, the smaller the standard deviation. And the deviation is a measure of the spread in the data. The deviation itself is the difference between the data values and the mean. The standard deviation is like taking the average of those, but we can't quite just take the average because they'll add to 0. Everybody okay with that?
Yes.
Then I'm going to go back to that homework question that says, so what would it mean if my standard deviation was 0? Let's go back and let's look at how we found that standard deviation. We subtracted the mean, squared them to make it positive, added them up, divided, took the square root. Well, if that square root was 0, doesn't that mean that this number would have had to have been 0? And for this number to be 0, wouldn't that mean that this number is 0? And if this number is 0, doesn't that mean that all of these, well, for positive numbers to add up to 0, non-negative numbers to add up to 0, wouldn't they all have to be 0? If the standard deviation was 0, wouldn't it mean that all of the numbers would have to be the same? Does that make sense? The only way that it could add up to 0 is if all of my data values were the same and they'd be the same as the mean. So write a sentence or two explaining that idea and why. And if the values are all very, very, very close to the mean, doesn't that mean that the standard deviation would be a very small number? As opposed to if the values were very far from the mean, wouldn't that mean that the standard deviation would be a very large number? Does that make more sense?
Yeah.
Okay, thank you for asking.
Mm-hmm.
Then I was a jerk and wrote over that page with that next few words written on it. And so I'm going to write them by hand. The next place we're looking at is the idea of, it wouldn't let me copy and paste, statistical inference. And when I look at statistical inference, I'm trying to use data to draw conclusions. So I talk about a population. And a population is going to be the set of all things being considered. And so when I cover this content with my contemporary math class, I always say, okay, so let's say I want to do a study and I want to know about how many math classes every college student in this country takes. And so my population would be every college student in America. So, would it be feasible for me to go and talk to or ask a question and get a response from every college student in America?
No,
No, why not?
because there's too many people.
There's too many people. By the time I finish getting that information from every college student in America, I'd probably have to start all over again because they would have all graduated and be a new group of students. It's frequently large, your population. And so, because my population is too large, I frequently use a sample. And a sample would be a subset of the population. Why use a sample? We'll use a sample when the population is too large, when the population is very large. And so, okay, let's go back to my theoretical example. I want to know how many math classes college students in America take. We've decided that all of the college students in America would be impossible for me to reach out to. So I'm going to come up with a sample, which is just a subset. Hey, I got this idea. All of you guys in my Zoom meeting, you're all college students, aren't you? Can I use you as my sample?
Yeah.
Would that be a good sample? Would this room full of community college students, I'm guessing you're all from Niagara County, New York, or near Niagara County, New York, Western New York. Do we have any dorm students with us from out of town, or are you guys mostly from Western New York?
I dorm, but I'm in Niagara County.
Yeah, okay. So people from Western New York, and you're all education majors. Do you think you'd be representative? Do you think what's average for you would be average for all of the college students in the country?
No.
You think you'd be a good sample, a fair sample? I don't think so. Not to trash talk you guys or anything, but I'm thinking, well, if I look at some of my advisees who are engineering students, they have to take an awful lot of math. And if I look at people like the nursing students in nursing don't take any specific math classes. So it runs the gamut. So it gets to the idea, well, what's a good sample? A biased sample would be not a good one. I think if I just used you guys, it would be a biased sample. It's not representative. Of the population. In that last section of the homework, there are questions about sampling techniques. I think one that's sort of a pet peeve to me is a self-selected sampling. Self-selected sampling is not good. That's when you decide if you're a part of the sample. I think one of the questions in the homework says that your representative in Congress wants to know the opinions of his constituents. By constituents, he means all of the people who live in the district. The people who voted for him, the people who didn't vote for him, all of the people who live in his district. And do you guys ever get in the mail at home a nice big glossy flyer with a picture of that politician on it? and they say, I want to know what you think. Here are 3 questions. Answer them and send it back to me. Do you guys ever get those in the mail?
No.
Yeah, do your parents maybe get them in the mail? I know we get them all of the time. And if you did get it in the mail, would you answer those questions and mail them back?
No.
No. Do you think most people answer those questions and mail them back? No. Who answers those questions and mail them back? Kind of like the,
People.
what?
Political people.
Political people, people with extreme views. If somebody's sent a flyer out saying, I want to know what you think about gun control. Well, those people who are like, strong gun advocates who have those signs in their front lawns, they might respond. Or maybe those people in Connecticut whose children died in a gun mass shooting, they might respond. But the average person probably won't. When you look at self-selected sampling, it's usually extreme views. And you know what? Talking about looking at things, I just looked at the clock, and you guys let me do it again. I'm running over because this is one of those things I can talk about a lot. Let's stop here because we just ran out of time. We'll pick up with this discussion when next we meet. Does anybody have questions on anything that we've done today?
No.
Okay, all right, then I'm going to